Okay, this is web assignment 4-1. Before we even start this one, I'll be honest with you. This one did not make sense to me, and this one took a while. So, a piece of insulated wire shaped into a figure 8 shown in the figure below. For simplicity, model the two halves of the figure 8 as circles. The radius. Okay, yeah. It's 3 centimeters down, the lower 7 centimeters. The wire has uniform resistance per unit length of 4 ohms per meter. Uniform magnetic field is applied perpendicular to the plane of the two circles in direction showing the magnetic field is increasing at a constant rate of 2.2 Teslas per second. Find the magnitude of the induced current in the wire. Here we go. R is equal to all right. Okay, so here we go. So this is just E equals out here, and then is it? And I equals E over R. Am I thinking of the different? I must be thinking of the different problem. No, I'm not. Okay, I gotta solve for you. There you go. That's what makes sense. Here we go. So this is some fun integral stuff, I believe. Or not integral, but at least derivative. That's my symbol. So equals the integral of b dA b dA. This font is screwing me up, so I'm gonna change it to purple. Okay, cool. Now here we take a derivative. This explanation is terrible. I'll go through it after I write all this down just to elaborate on what I'm just skimming over right now, but for the most part this is just what I'm going to do right now. Okay, so geez, that is a really thin font. Okay, so I wrote what it means, not what it means, but I believe that's flux, right? I believe that's flux. So the EMF is equal to the change in flux. Right? It's equal to the change in field, which is equal to the field. I think we have it as the change in field times the area. Now the change in field times the difference of the areas. I believe that's what we have to do here. And then in terms of what the areas of circles are, it's pi r squared, so now we're subtracting the areas of the circles. I'm sorry, this is, yeah, I just gotta, okay. And then now we can actually plug stuff in. I say stuff, I probably shouldn't say stuff, but you know. Then we have our value for the rate at which the field changes. 2.2 seconds. Times our pi, and then this is just, we're changing the meters here. And then 0.0276 volts. Then there's this equation here. Oh, that's the rate at which the, oh my god, that's the resistance. So resistance is equal to, so what is the derivative of the the rate at which the resistance changes. Okay, then we got ohms per, that's ohms, that should be ohms over meters. Times our 2 by, and this is just our radii. Okay, so hopefully I can explain this in my own words. So we know we had to use Kirchhoff's, right? I believe it's E equals IR, but we need to define current, so we need E or I equals EMF over resistance. We didn't have either of those, so first we had to find the volts. And we found the volts by taking the integral of, I think that's flux, right? Well, E equals the derivative of the change in flux over time. That's equal to change in field times the area, right? And we have a value for our change in field, and we just need to find our area values. Okay, and then using that, we found our E, so E equals, but now we need to find our resistance. Why is that? Oh, circumference. Oh, because the circumference would be the length of the wire. And that's why, okay, that makes some sense. Huh. Yeah, well, as you can see, this stuff is, well, personally at least, this is kind of where I'd like to say I've gotten better. I'd like to say, all right, let's just find an answer. I'll talk about my reflection later. Okay, boom. 0.01. Find the direction of the induced current in the wire. Select all that apply. This is one continuous flow of a wire, and we're always, directed inwards. I will start at the center. We have this kind of shape going on, right? Nope, that's not what I wanted. That's fine. We have that kind of a shape, and our field is in. Never use yellow. Why do I use yellow? And we're in. There's always going to be this in here. And since bad drawing. Okay. Let's assume they're all connected. They won't be in the same direction. So, I pairing of those two. So one has to be clockwise, the other has to be counterclockwise. No answer. Okay, in terms of reflection, yeah, I had looked this one up. I'm happy with the way I was able to walk through it. Not even walk through it, write it down and actually explain what was going on afterwards. That's a win for me, but yeah, electromagnetism and EMF and currents and directions is something I'm gonna have to continue to work on. But like I said, I was glad that I was able to walk myself through what I was actually doing after I did it.